Zhuangzhuang. I'm here to present our work AQUATOPE, Quality of Service and Uncertainty-Aware Resource Management for Multi-Stage Serverless Workflow. This work was done in collaboration with my colleague at Cornell University and my advisor from MIT. So I'll start with an introduction on the background. Serverless computing, also known as function as a service, is an emerging model for deploying cloud applications. In serverless, a function is a piece of application code uploaded by the user to the cloud. Functions get executed or triggered by events. Originally, serverless applications were built as simple single-stage functions, but nowadays, more and more developers are building applications as serverless workflows, where a group of serverless functions coordinate with each other to execute the application logic. By splitting a complex application into dependent but loosely coupled functions, the application itself can benefit from elastic scaling, load-based building, and modular development. So despite the increasing popularity of serverless workflows, the coupling of serverless application into multiple stages also introduced new challenges in resource management. So first, we have amplified startup overheads, which are caused by cascading co-stars across dependent functions. Second, workflows have large resource allocation space. Resource requirements can vary a lot across different execution stages of the same workflow. Additionally, even for the same function, warm and cold starts can lead to different performance behavior and resource requirements, making the resource allocation problem even more complex. Without proper resource allocation for each stage, the workflow can suffer from quality of service violation and increased execution cost. Finally, noise and uncertainty are inherent to FAS platforms. Large fraction of serverless applications have significant variability in invocation patterns. Noise and interference from co-located workloads also can lead to unpredictable performance, which cause biased observations and impairs the performance of sampling-based resource management approaches. So here we list some of the related works on resource management for serverless and cloud workloads. Most of this work focuses on independent functions or long-running monolithic workloads and assume noiseless Sutton with no interference. So now let me introduce the design overview. AQUATOPE is a resource scheduler designed for multi-stage serverless workflows. The design objective of our system is to meet the user-defined quality of service target while minimizing the execution cost. To achieve this, we jointly tackle the two correlated challenges in serverless, co-stars and resource allocation. First, AQUATOPE maintains a dynamic pre-warm container pool to minimize co-stars and ensure most of the function invocations are handled by warm containers. This can effectively reduce the resource allocation space to warm containers only. Then, it employs a container resource manager that allocates appropriate resource to each function based on its warm star performance behavior. We also designed both components to be noise aware and use spacing approaches to overcome the uncertainties that present in FAS platforms, which help AQUATOPE to maintain robust in the presence of workload fluctuations and system noises. In the following slides, I will try to explain these two components in detail. We will start with the dynamic pre-warm container pool. So our design objective is to maintain just enough warm containers to handle incoming requests, minimizing co-stars while avoid resource over-provisioning. AQUATOPE maintains a pool of pre-warm containers and uses a prediction-based container pool manager to adjust the number of pre-warm containers at runtime based on model prediction. To make accurate prediction and adjust the container pool accordingly, we need to incorporate external features, which can include time of day, day of week, and function trigger type information into time series prediction to improve the accuracy, and capture the seasonal trend in the function invocation patterns. We also need to make sure that the model is robust to noises and load fluctuations. To achieve this goal, we use a hybrid Bayesian neural network to infer future invocation rate. The figure on the right shows the structure of the hybrid model, which consists of an LSTM encoder-decoder and a prediction network. We use the LSTM encoder-decoder as an automatic feature extraction black box to extract the latent features from historical invocation patterns. The latent variable is combined with external features and feed into the prediction network to make the final prediction. We also leverage approximate Bayesian inference to incorporate noise and uncertainty into the model, so it can make accurate time series prediction even in the presence of noise and fluctuations. After making sure that most of the function invocations are warm starts, the resource allocation space can be reduced to warm containers only. In such case, we use a container resource manager to find the near optimal resource configuration for the workflow that can minimize the execution cost while satisfying the quality of service target. So instead of relying on a manually derived analytical model or searching out the entire configuration space, we take a data-driven approach, namely Bayesian optimization, to iteratively search for the optimal configuration. The figure on the right shows a snapshot of an iteration in the optimization process. The upper half of the figure shows the surrogate model, which is used to model the relationship between the resource configuration and the workflow execution cost. The lower half of the figure shows the acquisition function, which determines the next data point to be sampled based on the prediction of the surrogate model. BO works iteratively, so in each iteration, the surrogate model will be updated with the data sampled in the previous iteration, and the acquisition function leverages the updated surrogate model to determine the next resource configuration to be sampled. Then we can get the data points containing the resource configuration and the corresponding workflow execution metrics like performance metrics and execution cost. We use this data to update the models iteratively. So although BO itself is a widely used approach in other areas, applying to FAAS resource management still faces practical challenges. To solve these problems, we propose a customized BO workflow. So first, in our optimization workflow, we take noise and uncertainty into account by design. AQUATOPE uses noise-aware surrogate models and acquisition functions to account for both inherent Gaussian noise and use anonymity detection mechanism to prone the non-Gaussian data outliers, which can cause by resource contention, network instability, or background intermediate jobs. So this can help AQUATOPE performance model to remain robust in the presence of cloud noises and data outliers. So second, AQUATOPE effectively incorporates the end-to-end latency constraint into the optimization process by using a separate surrogate model that predicts the end-to-end latency and filter out the candidate configuration that might violate the quality of service target. So finally, we also enable batch sampling with customized acquisition functions, allowing it to sample multiple configurations in parallel, substantially reducing the exploration time. So here we show the system architecture of AQUATOPE. So we built our system over Apache OpenWhisk, which is a widely used open source FAS platform that powers IBM Cloud Functions. Figure on the right shows our system implementation. We modified OpenWhisk to support dynamic adjustment of the pre-warm container pool and decouple the CPU and memory allocation for each function. Compared to the original architecture, we also add a container pool scheduler to dynamically resize the pre-warm container pool at 1-minute interval. We also create a container resource manager to search and update registered workflows resource configuration. So for the evaluation, we have used representative serverless workflows as benchmarks, which include generated workflows in fan-in and fan-out patterns, data processing pipelines, and like ML pipeline and video processing pipelines, and interactive app application like social network from Desktop Bench. We use Locus as the workload generator to emulate real user traffic based on Azure function dataset. We deploy our system to a dedicated local cluster with 5 40-core servers and 288 core servers to conduct the evaluation. So we first evaluate AQUATOPE's two key components separately. For the dynamic pre-warm container pool, we compare to alternative approaches, including fixed keep alive, autoscaling, histogram-based approach, FAS cache, and icebreaker. The figure on the left shows the average cold start rate, and the right figure shows the aggregated preparation memory time. So we can see that AQUATOPE can significantly reduce the cold start rate while reducing over-provisioned memory. The underlying reason is that for serverless workflows with complex topology and invocation patterns with high variation, our hybrid model can still make accurate prediction, allowing it to make fine-grained and timely adjustment to the container pool. We then evaluate the resource efficiency of AQUATOPE's container resource manager by comparing it with alternatives, including random search, autoscaling, and a naive Bayesian optimization-based resource manager called CLIDE. The diagram in the slide shows the workflow execution costs for different workloads managed by different resource managers. And we can see that across all benchmarks, AQUATOPE constantly outperforms prior approaches and finds a near optimal resource configuration that can minimize the execution cost while satisfying the quality of service target. The underlying reason is that for complex serverless workflows, AQUATOPE customized BO workflow can better incorporate the end-to-end latency constraint in the search process. The noise handling mechanism also allows us to remain robust in the presence of interference and data outliers, making it capable of converging to the most efficient resource configuration fast. So then, we first demonstrate that the resource manager cannot achieve the desired performance without reducing the resource allocation space to warm start containers. So we compare the performance of the fully fledged AQUATOPE with a simplified version with only the resource manager in place. And the figure shows that for the simplified version, it suffers from a dramatic increase in terms of the CPU and memory time. This is due to the diverse behavior of cold and warm starts in a workflow, which lead to different resource requirements. And the simplified version will be forced to strike a balance between them, leading to degraded performance. This indicates that cold starts and resource allocation are correlated problems and needs to be tackled jointly to achieve desired performance. Finally, we perform an end-to-end analysis of AQUATOPE by comparing it to a framework using auto-scaling-based approach and a framework combining the container pre-warming mechanism in Icebreaker with a BO resource manager in C-Lite, which are the best performing alternatives. The figure shows that the average quality of service evaluation rate and the aggregated CPU and memory time for different frameworks. And we can see that our system outperforms the best performing prior approach, eliminating up to 39% of the quality of service violation and bringing the total down to below 3%. We can significantly reduce the CPU and memory usage, reducing the CPU time by up to 55% and the memory time to up to 64%. So in conclusion, we can achieve these benefits because we are jointly tackling the cold start elimination and resource management. And we use Bayesian approaches and build Bayesian models that can adjust to the behavior of a given application while remaining general and robust to cloud noises. That's the end of my talk, and I'm happy to receive any questions. Thank you.